To simplify this first one, you've got some options, but the way I like to do this is to use properties of exponents to move everything around. So let's see how that might work. This first problem is worth 3 points. So we're going to break this up. We want to write this in the form a number times x to a power times y to a power. So the number can be 2/3. All right. And now I need to get everything upstairs, so x to the minus 1. And that x to the 4 downstairs can be an x to the minus 4 upstairs. The cube root of y is y to the 1/3. And then y to the minus 2 downstairs becomes y squared upstairs. Now we need to combine these exponents. When the bases are the same, like here, I can add the exponents. So x to the minus 1 times x to the minus 4 becomes x to the minus 5 by adding the exponents. Similarly, the y becomes y to the 2 plus 1/3. 2 plus 1/3 is 7/3 if you stop to get a common denominator. Don't make the mistake of multiplying exponents here. A number of people had 2/3 for the answer, 1/3 times 2. But you have to add the exponents when the bases are the same. So this becomes 2/3 x to the minus 5, y to the 7/3. All right, in this next one, we want to investigate some limits. The limit as x approaches 2 from the right of f of x. So we go on the graph to where x is equal to 2. That would be right about here. 1, 2. Let's see, 1, 2. All right, as x approaches 2 from the right, so we're coming to 2 from the right, and we hop on the graph, and we arrive at a height of 3. So the answer there is 3. All right, as x approaches minus 3 from the right, so minus 3, 1, 2, 3. As we walk towards minus 3 from the right on the function, we arrive at a height of 0. As x approaches negative 3. Well, that depends on which side we're on. We just saw if we approach from the right, we're going to be at a height of 0. If we approach from the left, we're going to be at a height of minus 2. So this limit does not exist, because we have different left and right limits. The limit as x approaches 4. So if we look at our graph here, as x approaches 4, 1, 2, 3, 4. As x approaches 4 from the left or from the right, we're going to arrive at a height of 2 if we hop up on the function here. Doesn't matter what's going on right here, all right, at the point. What only matters is what happens as we get close to x equals 2. We're going to arrive at a height of 2. I'm sorry, close to where x equals 4, we arrive at a height of 2. Finally, the limit as x approaches 0. As x gets close to 0 from either side, this way or this way, the function is headed towards plus infinity. So don't write d and e, since we can see from both sides that it's going to infinity. We'll just write infinity here. All right, the last one, as x approaches 2 from the left, 1, 2. From the left side, we're approaching minus infinity. Does something different from the right, but this is just a left-hand limit, so that's all we care about, and we write minus infinity. If you can do a limit as infinity or minus infinity, that's what you should indicate, not simply d and e. Solve the inequality. This was probably the problem on the quiz that almost everybody had the most difficulty with. All right, but this is an important kind of problem. You'll find some more examples on the Algebra Review worksheet, and it would pay attention to those. For much of the book here, Chapter 4 in particular, we're going to be looking at things that are similar to this inequality. Now, the first error that a number of people made is to multiply through on both sides by x minus 3. You can do that if you're very, very careful, but here's the trouble. If x minus 3 happens to be a negative quantity, That would happen whenever x is smaller than 3. Then when I multiply both sides by x minus 3, all right, multiplying both sides by a negative reverses the inequality. All right, so we've just made the problem a lot harder. What we want to do instead is collect everything on one side of the equation and compare to 0. In general, it's a bad idea in inequalities to multiply through or divide through by anything containing a variable. So let's see what we can do here. Well, if I move everything to one side, you could also do it the other way. Now I have to get a common denominator, so I'm going to multiply the 2 by x minus 3 over x minus 3 and put it together on a common denominator. So we've got and now this quantity here I need to be less than or equal to 0. Let's clean that up and see if maybe we can factor things. X squared minus x minus 2x is minus 3x. Minus 10 plus 6 is minus 4. Factoring the numerator. All right. Once we have this in factored form, then we can look at each of the factors to see how it changes sign and how that makes the overall quantity, the overall expression here, negative sometimes. All right. What you don't want to do is just try and guess. It looks like something's going on x equals 4, something's going on x equals -1, and so on. My favorite way to do these is by using a number line and test points. So if we start with a number line, I can see here that if I plug in x equals 4, I get 0. If I plug in x equals -1, I get 0. And if I plug in x equals 3, the expression is undefined. So all three of those locations, 3, 4, and -1, are places where this quotient could change sign. All right, where it's equal to 0 or where it does not exist are places where this could change sign. All right, and that's of interest to us because we want to know where the sign is negative or where the expression is equal to 0. So let's mark those all in. We have -1, 3, and 4. It's 0 here, it's 0 here, and the function is, or the expression is undefined there. Now here's the wonderful thing. On each of these remaining parts of the number line, the sign can't change at all. Right? The sign of this expression here cannot change. So if I determine the sign on each of these subintervals at one single point, that sign is good for everything. From each interval now we need to check a test point. So from the interval from 4 to infinity, I'll check x equals 5. So if we plug 5 into our expression, 5 minus 4 is positive. I don't actually care if it's positive or what the exact value is. I just want to know the sign. 4 plus 1 is positive. 4 minus 3 is positive. Positive, positive, positive. So at x equals 5, the expression is positive. Therefore, everywhere to the right of 4, the expression is positive. Now we need to check another number between 3 and 4. Say x equals 3.5. 3.5 minus 4 is negative. 3.5 plus 1 is positive. 3.5 minus 3 is positive. 1 negative times a positive divided by a positive is negative. So from 3 to 4, the expression is negative. Between -1 and 3, we could check a value. Say x equals 0. At x equals 0, we've got -4, so we have a negative. 0 plus 1 is positive. 0 minus 3 is negative. Negative over negative is positive. Lastly, let's check something like x equals -2. -2 minus 4, negative. Minus 2 plus 1 is positive. Minus 2 minus 3 is negative. Hang on. Minus 2 plus 1 is negative. Minus 2 minus 3 is negative. 3 negatives does make a positive. 3 negatives makes a negative. Sorry. All right, now we finally have it straight. Okay, so now we want to know where the expression is less than or equal to 0. All right, it's less than or equal to 0 between 3 and 4, not including 3. Can't include 3 because the expression isn't defined there. Including 4 because it's equal to 0 there. Likewise, from minus infinity to 1, minus 1 is included, also including negative 1. So our final answer in interval notation, minus infinity up to negative 1, union 3 to 4. Good. All right, to evaluate these limits, the first thing we do is plug in to see how we're doing. So we get 3 squared minus 9. 3 squared plus 2 times 3 minus 3. This is 0 over 12. All right. So 0 over 12 is simply 0. So this one, we're all done. We just use direct substitution. And we evaluate. It's 0 over 12. Zeros are bad when they're in the denominator, but no problem in the numerator. The value of this limit is simply 0. Notice here that we didn't have to carry the limit symbol around or along because step 1, we just used the direct substitution property. You get rid of the limit symbol at the point when you plug in the value of x. This next one isn't quite as simple. If you were to evaluate this at 3, 3 squared minus 9 is 0. Minus 3 squared minus 9 is 0. Minus 3 squared plus 2 times minus 3 is, again, 0. All right, you can double check that. All right. That means I cannot use direct substitution because I have an indeterminate form of the form 0 over 0. Indeterminate means I have to work a little harder to determine what's going on. So we're going to factor and cancel. The numerator is a difference of squares. The denominator factors. The x plus 3 term cancels. Notice the x plus 3 term is exactly what's causing us trouble. When I put in minus 3 there, I get 0. When I put in minus 3 there, I get 0. All right. But since we're talking about x not equal to minus 3, but x gets close to minus 3, this is not 0. This is not 0. It's some quantity divided by the same quantity, and I can cancel it off. And now I'm in a position to use the direct substitution property. Right? Since what remains here is not 0 when I plug in minus 3, I just plug in. So the answer to that limit is 3/2.